In this webinar, we're going to be looking at a topic that I'm titling Dispelling the 802.11ac Myths of Speed. And what we hope to accomplish here is an understanding of actual performance expectations out of even a modern 802.11ac wireless LAN. My name is Tom Carpenter, and I'm the CTO here at CWNP, and I'd like to welcome you to this webinar. This is a re-recording of a previously live webinar that we've created due to some technical difficulties. For further information about our organization, you can always visit the website at cwnp.com. All of our webinars are archived here on YouTube at CWNP TV, and of course you can follow us on Twitter at CarpenterTom and at CWNP. So what are we talking about here today? What we're looking at is two topics, one result. We'll get to the result in the end. The two topics are uplink requirements and multi-user MIMO realities. So we're looking at uplink requirements in order to understand real performance expectations for an 802.11ac wireless LAN. Many people tell us we need very fast uplinks because of 802.11ac's potential, and we want to talk about that and address the real-world issues. Then we're also going to talk about multi-user MIMO, and we want to look at it from a reality perspective to see what we can expect out of actual performance gains from this technology. So the thing is that we see a lot of things, numbers like 1900, 1750, and even 7200 on tri-band routers today. So what do they mean? Well, the hint here is that they're very misleading, and we'll see why. The next question then is, what throughput can I expect from my 802.11ac AP? Well, the answer is going to be far less than the highest potential data rate, which is what we're often sold on. And finally, do I really have to upgrade all of my switches to 10 gigabit per second Ethernet, or at least 2.5 or 5 gigabits per second? Well, maybe, but it's not likely as urgent as you may think based on what you've heard from marketing materials and so forth. So let's take an example. Just listen to this, and I have redacted the name of the device, but other than that, except for the light gray parenthetical text, this is actual marketing material from an actual device sold in the consumer space. It says game, share, and stream in 4K on Wi-Fi faster than gigabit Ethernet with the particular model that we're talking about. Now the first thing is it says faster than gigabit Ethernet. Really? Well, we'll see as we go through here. The wireless router runs multiple bands. It has three, in fact, one in the 2.4 gigahertz band and two in the 5 gigahertz band, to reach speeds up to 7200 megabits per second. Speeds or data rates? And what does speed actually really mean in the real world? And can a single client get those speeds? Or is that one client in one band, another client in another, and another client in another? And therefore, no single client is going to reach speeds up to 7200 megabits per second. But anyway, we're going to do this while providing whole home coverage. Its leading-edge antenna design sends strong, reliable Wi-Fi across your home, and new beam steering technology directs Wi-Fi along the clearest path to devices. You gotta love this speak, don't you? The clearest path to devices. Well, it's going to direct it based on an understanding of the RF space, but it's a lot more complex than just the clearest path. And then it says the router uses multi-user MIMO. Look out, we've got a buzzword here, but we're not defining any value. And 4 streams, here's another buzzword, to reduce wait times and increase Wi-Fi speeds. A powerful 1.4 gigahertz dual-core processor easily handles simultaneous connections to keep your router running at peak performance. That last sentence is probably the most accurate of them all. The point is, this is marketing speak, and this language can be misleading. It makes you think you're going to get something that you may not be going to get. While the device represented here is a wireless router aimed mostly at the consumer market, we see some of this language coming out of enterprise vendors as well. They love the highest data rate possible marketing type language, and the highest data rate possible is just not the real world. So therefore, we need to understand these issues. So 802.11ac uplink requirements, why discuss it? Well, it's important to understand the issues. We should always underpromise and overdeliver in actual implementation. So we don't want to promise some expectation of performance that's just not practical for the real world. And also, it's an excellent learning exercise. So when it comes to the uplink, what we're talking about is the link between the wireless AP or router and the Ethernet network. Now let me be very clear here at the onset. What I'm not saying that you should implement only 1 gigabits per second links. You can implement multiple 1 Gbps links, 10 Gbps links, or any other speed in between. If you have them, sure, use them. Go ahead and install them. But don't promise that you're getting the speeds that actually warrant or demand that greater than 1 gigabit per second uplink. Instead, understand your environment and commit to what you can accomplish in that environment for your wireless LAN. So to understand the issues, we need to start by understanding data rates and from what they are derived. So data rates are derived based on the modulation that's in use. And the modulation that's in use is dependent on the conditions of the RF link. That is, I can't use a modulation that needs a very clean and clear signal if I don't have a very clean environment and a clear signal. So we measure that by something called signal-to-noise ratio, or SNR. And an SNR, or SINR, signal-to-interference and noise ratio, is a measurement of the space between the noise of my environment and my actual signal that I'm receiving. I need more space between the noise and the signal if I'm going to get the highest data rates, and less space for the lower data rates as we step down. Data rates are also defined by, in addition to SNR, the width of the channel, like 20 megahertz, 40 megahertz, 80 megahertz, and so on. The length of the guard interval, which can be either 400 or 800 nanoseconds in 802.11, and the number of spatial streams, which can be 1, 2, 3, or potentially 4 in today's devices. So all of this comes together to give me, in the end, the actual data rates that I have on the network. Now, the reality is that there are several devices out there today that support 3 spatial streams, and we could use a 40 megahertz channel and a 400 nanosecond guard interval. The maximum data rate we would get out of that, even with 802.11ac, is 600 megabits per second. The lowest, just staying with the MCS data rates, modulation encoding scheme data rates, is 45 megabits per second. Of course, because we're in the 5 gigahertz band with 802.11ac, we do still support the older 802.11a data rates of 54, 48, 36, and so forth. So, because clients and not the APs actually constrain what can be used in relation to AP features, today's reality is a 3-stream 40 megahertz channel for most enterprise deployments. Most enterprise deployments do not use 80 megahertz, or certainly not 160 megahertz channels, and many use 20 megahertz channels, particularly in high density or very high density. Now, in addition to that factor, most clients are not 3-stream, but we're going to give the benefit of the doubt and go with 3-stream as our starting point in this presentation. Now, we could go up to 4 spatial streams and 40 megahertz, still a 400 nanosecond guard interval. We'd look at a maximum data rate now of 800 megabits per second, and we would step down to 720 and then 600 before we get to the same maximum data rate we had with 3 spatial streams. But what if we raise this? Now, before we do, let's point out the fact that this is kind of the maximum you would expect to see in a typical enterprise deployment today, because we're not deploying 80 megahertz channels, we're deploying 40 megahertz channels or 20, and 4 spatial streams is the maximum that you would see in Wave 2 802.11ac devices. So we're not going to see anything above this, but let's go higher still. Here we're looking at 4 spatial streams and an 80 megahertz channel. Now, in this case, I can get 1,733.3 megabits per second as my maximum data rate. You can see I'll step down to 1560, 1300, 1170, 1040, and so on as I go down. Now, this is not at all real world, because we're not going to be implementing 80 megahertz channels in the vast majority of deployments. There might be some corner use case scenarios where you would, but in the vast majority of cases, we're doing 40 megahertz channels or lower. And because of that, these data rates are not real world, but I want to show you the numbers that are often being used. Now, I'm not even showing you here the 160 megahertz channel at this point. This is the 80 megahertz channel. Now, with that said, if we stay with the best case scenario for 802.11ac in an enterprise deployment, which is an 80 megahertz channel, 400 nanosecond guard interval, 4 spatial streams, even assuming all of our clients support 4 spatial streams, here's the real world. The real world is that clients are scattered all over the cell. The clients are not all nestled up nice and cozy up against the AP, getting to know it very well at 1733.3 megabits per second, which means they've got the best signal-to-noise ratio. They are able to do 256 QAM. They are able to use the coding scheme that gives the most data for the throughput. All of that is true, but only for a few clients. As you can see here, we've got several clients that are connected to our AP. The vast majority of these clients are at 1040 megabits per second and lower, and that's the data rate, We can see that a significant number are below 780. Overall, our average data rate here is probably somewhere around 600 or 650 megabits per second. But you can see we're even giving the 80 megahertz channels in this case. And we're assuming all of these clients are for spatial stream clients. Neither of those things are actually done in the real world. So when you keep that in mind, it really brings this into perspective. Now, consider the odds of a station using the highest data rate here, the 1733.3 megabits per second. Remember that lower data rates cover more space than higher data rates. The highest of data rates are only a very small portion of the cell size. The lower data rates are the larger portion of the cell size. Statistically, therefore, it's more likely that you'll have the vast majority of your clients at data rates at least 3 or 4 steps down from the highest data rate that the AP has to offer. This is even true if you start to adjust output power levels and things like that, because all you do is reduce the overall cell size, and at the same time, you're making it so that the area where the highest data rates can be used is also reduced. So we're still going to see the stations in the cell using data rates that are 3, 4, 5 steps off of the highest data rate for the majority of the clients that are in that cell. So all of this is said to get a real picture of what it would be like even with 80 megahertz channels. Now remember, we're not factoring in here the stations that could be connecting with 802.11a rates. So they could be connecting at those even lower data rates as well, because we're assuming these are all 11AC for spatial stream clients, and they would roam to another AP before going down to those data rates. We're assuming the best case scenario with a perfect design in our wireless network. Now let's bring all this together. Here's a throughput reality check for 802.11ac. We have here a simple formula. It doesn't include absolutely everything, but it gives us a good talking point. We have the average client data rate times the utilization rate times an overhead factor, and this gives us our average Ethernet throughput. Now let me talk about the overhead factor for a minute. This value, you could say, is the flip of management and interface overhead in our formula. So if the management interface overhead is 30%, which would be wildly conservative, the overhead factor is 70%. So in other words, we only get to use 70% of what we're calling the data rate to accomplish actual useful throughput, right? The reality is that due to co-channel interference, adjacent channel interference, and standard overhead, the acknowledgement frames, the probe request and response frames, the beacon frames, all of these other management frames that are used on the wireless medium consume much of the airtime, and therefore the overhead is probably somewhere 50 to 75% in that range. But usually we're going to see that it's down somewhere closer to 60, 65% in many of our even newest networks today. This doesn't even account for the fact there could be an interfering signal out there consuming some of the airtime so that we cannot have 100% of the airtime. So here's an example. We take a 1300 megabit per second data rate, 90% utilization rate. So we're actually using the airtime 90% of the time. That means 10% is either consumed by an interfering device or 10% is just not used. And then we have 70% overhead factor. That means only 30% is overhead, so our overhead factor is 70%. This gives us 819 megabits per second. Now keep in mind, this is an exaggerated average. That's not going to be your average data rate. This is an exaggerated utilization. It's not usually that high. And this is a conservative overhead factor. It's usually going to be a lower percentage than this. But you could see 70, even 75% in some scenarios. Now, based on these calculations, you might quickly say, wait a minute, what if I have two 5 gigahertz 802.11ac 4 spatial stream radios and a 2.4 gigahertz radio in my IP? So I've got 3 radios. Wouldn't this put me in a bad situation? Or even if I'm using something a bit more sensible and I've only got 2 radios in an enterprise deployment, wouldn't this put me in a potentially bad situation? Well, remember, we're talking about exaggerated average and exaggerated utilization. And we're talking about the fact that this is an 80 megahertz channel, which is probably not going to be used for the vast majority of deployments. So let's get back to a calculation that might be based on a real world data rate we could see. So here's 3 spatial streams. Now this would even still assume all your stations are 3 spatial streams to get an average. But what we're going to do is we're going to pull only 2 steps down from the highest data rate, 450 megabits per second, and we'll use that in our formula. So 450 megabits per second with 70% utilization and 65% for the overhead factor, we end up with 204.75 megabits per second. That's the final data rate we get out of our radio or I should say it's the final throughput that we get out of our radio when deploying this. And so even if I have two 5 gigahertz radios, I'm not going to get that 204 megabits per second out of my 2.4 radio. So even if I assumed I did, we're still looking at around 615 megabits per second for all 3 radios, even in a tri-band device. So as you can see, we haven't gotten up to our 1 gigabit per second Ethernet link, have we? And this is a very important factor to consider. So what we're seeing is in a real-world calculation, and in a real world, we're not going to use tri-band radios, at least not right now, in enterprise deployments. So we're looking at somewhere around 500 to 700 megabits per second as our very likely peak that we could accomplish. It is important to point out in this case that you could have a situation where you do have a client who is very close to the AP, and that client is not going to be able to burst for a few moments above the maximum throughput potential that you have in the channel. And so it is possible that the buffers of the AP for that one client in some kind of an aggregate frame throughput could end up not being able to utilize all of the throughput that it could accomplish because of a limit on the Ethernet side, but that's going to be a very rare situation indeed. Now, we've talked a little bit about the uplink and some of the real issues with throughput. Let's talk about the other factor that we saw in our tri-band marketing literature, and that was multi-user MIMO. Now, multi-user MIMO is an interesting technology. It's beneficial, but is it as beneficial as you might think? Okay, so here's the definition. With multi-user MIMO, an AP transmits frames to multiple clients concurrently rather than in sequence. So I don't have to send to my one client and then to my other client. I send to both of them at the same time. It is an 802.11ac downlink only. The plan is to make it uplink as well in 802.11ax, but right now in 802.11ac, it is downlink only. So since a significant portion of our traffic, 80 to 90%, is downlink, it's probably a really good thing, right? Well, there are some basic requirements of multi-user MIMO. First, the clients have to support it. Second, you have to be in the right conditions for grouping. Third, you need fairly stationary clients, and I'll explain why. And fourth, data destined for multiple clients in the group. So not only do they have to be in the group, there has to be data destined for multiple clients in that group. So let's talk through these issues. First of all, you have to have client support for multi-user MIMO. The required client support is an 802.11ac PHY, clearly. They need to be able to respond to transmit beamforming. So transmit beamforming response capable and enabled, and a single stream client can participate. So this is not just multiple stream clients, because one stream could be transmitted as a multi-user MIMO transmission to a single stream client. So multi-user MIMO uses explicit beamforming, which was first introduced in 11n but standardized in 11ac as the only beamforming supported by the standard. This sends sounding frames to discover the client conditions. So the AP sends out these frames to ask the client to tell the AP what it sees when it receives those frames. The client supports transmit beamforming and responds to these sounding frames, and so the channel conditions can be understood by the AP. Now, older clients do not support multi-user MIMO. 802.11ac Wave 1 may or may not. 802.11n and earlier, of course, do not. The percentage of clients supporting multi-user MIMO in most environments is still very low right now, but this will change over time. So right now, this is a factor that says there aren't as many clients out there that'll do multi-user MIMO for you, but over time, we certainly will see this change, to be fair. Next, you have the issue of multi-user MIMO groups. A multi-user MIMO group simply means that multiple stations that support transmit beamforming for multi-user MIMO are in optimal conditions to receive multi-user MIMO streams. These conditions, by the way, are called channel state information, or CSI. And so an AP may determine that we can put these two stations in a multi-user MIMO group and these two stations in a multi-user MIMO group. Now, there is some misunderstanding out there, probably because of vendor demonstrations that have been done, that says the devices have to be on either side of the AP, because that's usually how vendors set things up to demonstrate. But that's not necessarily required. They just have to have RF conditions so they can be in a multi-user MIMO group. Now, there may be more than two in the group. It's not just two. There's a maximum of 3 concurrent multi-user MIMO client transmissions for best performance that most chipset manufacturers recommend. A maximum of 4 is allowed. So we could have more than 2 in a group, but we just have 2 pictured in our groups here. So what this means is that multi-user MIMO Group 1 could receive simultaneous data to both of those stations, and multi-user MIMO Group 2 could receive simultaneous data to both of those stations at the same time. So this is how the groups actually function. Next, we have the issue of stationary clients. Now, when a client participates in a multi-user MIMO group, that client is participating in the group because the conditions are right. The issue then is that when a multi-user MIMO client moves, the conditions at their new location change. And it could be a move of just a few inches or feet that could change those conditions. And it may result they could no longer participate in the same group, or at least receive transmissions at the same time as the other station they could have received transmissions with. Additionally, as frames fail to be acknowledged, because they're not getting through to the multi-user MIMO station, some mechanism has to address this. We could lower the data rates. We could remove them from the multi-user MIMO group. We could perform a new beamforming exchange or sounding exchange. We could just disallow participation altogether. This is going to be the secret sauce of the APs. So they could decide, well, that station moves around all the time. It's causing too much overhead. We're not going to allow it to participate in a multi-user MIMO group. This sounding process happens very frequently, and it happens again. There is not necessarily a trigger that says it has to happen. It just has to happen periodically. But then obviously when frames cannot be delivered, the AP can make an assumption, okay, maybe it's not in the same position anymore and it can't receive in this multi-user MIMO configuration that I have them in. Now, the estimation of overhead for sounding information is less than 1% of airtime, but more stations using multi-user MIMO makes this an important factor, and there is overhead there, and there can be situations where clients have to be moved out of groups and so forth in order for this to continue functioning appropriately. Now then, the final requirement was, remember that we have to have data for multi-user MIMO clients. So the data has to be available in the cache of the AP for all stations receiving simultaneous frames. So I can't really say, well, I'm going to use a multi-user MIMO group here and send data to station 1 and station 2 if I don't have data for both station 1 and station 2. Frames should also be relatively the same size for ultimate airtime optimization. Otherwise, I'm sending a very short frame to station 1 and a long frame to station 2, and I'm not really getting as much benefit from multi-user MIMO. That's particularly true if, because I'm using multiple streams to send to multiple clients, that I'm using lower data rates, because there's a 3 dB difference. That is, it may lower the data rate because of a 3 dB difference in requirement for SNR when sending the multi-user MIMO streams to the different stations. And it might have been faster to send the very short frame to station 1 at a higher data rate and then the longer frame to station 2 at a higher data rate. So this is all the complexity that must be understood and calculated by the AP. In the end, AP is going to have to use some buffer method rather than just direct forwarding of frames in order to have something available for these stations. So for example, we can see that data may come in such that there's something for station 1, then 2, then 4, then 2, then 1, then 3, then 4, then 1, and so forth into the AP. And as this traffic comes in on the Ethernet port of the AP, it's going to have some buffering mechanism so that it can say, okay, I've got 2 frames here for station 1 and station 2, but then it's station 4 and station 2, which are not in a multi-user MIMO group. So maybe I'll hold station 4 in the buffer and wait until I get something for station 3, which does come in shortly. But then there's the issue of how long do I wait? What kind of traffic is it? Can I wait when it's QoS traffic versus non-QoS traffic? All of these factors must go into the secret sauce of the AP and how it chooses to implement this algorithmically. So this brings us to our one result. In the end, remember that data rates do not equal throughput. Data rates are simple in comparison to understanding throughput. Now, there's complexity there too. You've got to understand it's about modulation and coding and spatial streams and channel width and guard interval length and so forth. But compared to throughput, it's rather simple because throughput is complex. We have varied data rates all over the cell, which result in longer wait times even for higher data rate clients. So if a low data rate client at the edge of the cell is transmitting a frame, the higher data rate, more toward the center of the cell, that station is unable to transmit while it waits on that other data rate. So even though it can send at a high data rate, it can't send it right now. It has to wait its turn. And then there's interference, both co-channel interference, which is really contention, adjacent channel interference, or even non-Wi-Fi interference. This impacts airtime availability. And then there's 802.11 management overhead that's still there. So all this brings the throughput way down. So when we talk about speed in marketing literature, we're talking about data rate. And usually we're talking about the highest possible data rate you could ever hope to get. When we talk about throughput, that's what really matters, and it's usually nowhere close to the maximum data rate of an AP or client. Then 802.11ac is better than past PHYs in hardware, and we do want to keep this in mind. Data rates are higher, so that does make throughput higher. Multi-user MIMO does provide incremental gains, so that also gets us better throughput overall, though not as much as some might think. chipsets are improved. So even without the higher data rates in multi-user MIMO, the chipsets are improved and do more efficient and better processing. Antenna design is improved, helping us to pick up signals with better SNR. So all of these things come together to be able to say that 802.11ac is far better than past PHYs. But it doesn't give the improvements in actual throughput that many expect due to information often distributed or improperly understood about the technology. Because marketing is about marketing and selling you something, but designers, we have to speak the truth. We have to tell people exactly what they can expect out of their network. And the reality of expectations for 802.11ac, even Wave 2, even with a few 4x4 client stations out there, is generally nowhere near 1 gigabit per second throughput on the wireless side of the link. So make sure you keep that in mind when you're evaluating the performance expectations and communicating those performance expectations to your customers, to your internal users, and so forth as you implement, support, and manage 802.11ac networks. Thanks for viewing this webinar.